So let's review acids and bases. Many years ago, acids and bases had a very simple definition. Acids were substances that tasted sour, like the juices of a lemon, and bases were substances that tasted bitter. So here are some common. Fruits contain a lot of acids in them. For example, there's an acid in lemon called citric acid. Baking soda is a common base. This stuff here to remove hair contains calcium hydroxide, which is a base. But obviously, to determine if these are acids or bases, tasting them probably isn't the best process. There must be some other process, and today there is. So, how do we define acids and bases today? It's not simply something that tastes sour or tastes bitter. Acids are substances that will increase hydronium concentrations in a solution. Hydronium is actually this ion here, H3O+, but we abbreviate it to H+. So we'll often say increases hydrogen ion concentration in solution. So here you have an acid. There's an arrow showing that it's dissolving. This is a two-way arrow because this reaction goes both ways. But what matters is that you understand that this is the acid starting with an H, A over here. And when it dissolves, there's more H plus in the solution compared to what there was before. So acids, when they dissolve, we say they ionize because they're not really ions at first. If you think about it, HCl is a molecular compound, which means there's no ions in there. So they have to turn into ions. So HCl, when you put it in water, will ionize, will become H plus, that's an H there, and Cl minus. But the point is that hydrochloric acid increased the concentration of H plus in the solution. So acidic solutions will have a higher concentration of H plus compared to hydroxides. And if you think about it as well, those are the parts of water, HOH. Water, pure water, has a pH of 7, is neutral. But as soon as you increase one of these, this or this, then we either have an acid or a base. If you have more of the H plus compared to the OH minus, then you have an acidic solution. How do you make acids? Well, you take a non-metal oxide, react it with water, and it produces an acid. So a non-metal oxide would be, for example, carbon dioxide. That's a non-metal oxide. It's a non-metal combined to oxygen, reacts with water, and makes carbonic acid. In this image, you can see that we put acid in some water, and the acid ionized to form H plus in the solution. So we have a higher concentration of H plus compared to what we had before, which makes that solution acidic. I mentioned pH. pH is a measurement of acidity. We'll see it in more detail later, but for acidic solutions, the pH is less than 7. So if you have a pH of 0, 1, 2, 3, 4, 5, 6, 6.8, 6.9, that's all acidic because it's less than 7. Bases, they increase hydroxide ion concentration. So hydroxide ion concentration in solution. And hydroxide, remember, is OH minus. So NaOH is an ionic compound. It's a base. We know that because there's no H there. It dissociates. Because it's already ionic, it can just split into its ions. It'll form Na plus and then OH minus. So it increased the OH minus ions in solution. So if you look at water, that's the other part of the water. So a basic solution has a higher concentration of OH minus compared to H plus. By the way, these square brackets mean concentration. You can think of it as amount for now, or amount in a volume. We did talk about ammonia being a base. There's no OH, but it's a base. And this picture illustrates why. Ammonia has these electrons over here that takes H away from water and then makes this ammonium here. But the fact that it took H away from water means that the water was now converted into OH minus. So ammonia is a base because it indirectly increases the OH concentration in a solution. And you can see a whole bunch of other examples of bases over here. So Windex, which contains ammonia as a base, bleach as well, Drano, baking soda. Those are all examples of bases. How do you produce bases? Well, instead of a non-metal oxide reacting with water, it's a metal oxide reacting with water to produce a base. So for example, here I have sodium oxide. It's a metal oxide because it's metal with oxygen. Reacting with water produces sodium hydroxide. So a metal oxide reacting with water will produce a base. So acids and bases have properties to tell them apart. They have different properties. As we mentioned earlier, even though we don't do this in the lab, acids taste sour. Bases generally taste bitter. For characteristic for the touch, bases are slippery to the touch, almost like soap. So they're soapy. But acids, there's no characteristic texture. These both conduct electricity. As long as they're dissolved in water, they both conduct electricity. The pH of an acid is less than 7. I didn't mention this on a previous slide, but the pH of a base is more than 7. The ions produced by the acid in solution are H plus ions, and the ions produced by the base are hydroxide ions. So this is hydronium or hydrogen ions, hydronium, and these here are hydroxide ions. So acids ionize to form H plus in solution. That's our summary there. Acids can be binary acids, and then bases, they dissociate to form hydroxide ions. Acids can also be oxyacids. But the point is that regardless of what type of acid you have, we increase the H plus concentration, and for the base, we increase the OH minus concentration. Bases usually have hydroxide in, but they can have other things like bicarbonate, or they can be things like NH3. You won't have to know all the exceptions right now, just understand NH3, that's the base and why. Indicators are substances that change color to let you know if you have an acid or a base. And so they're quite useful because many times when we do an acid-base reaction, there's no color there. So we have to add a color in there. So you can see the indicator test over here. We use this paper called litmus paper. And what happens is the red litmus paper will turn blue. Whoops, I should do that in the base section. Let's erase this. Red litmus paper will turn blue in a base. Will turn blue in a base, but it'll stay red in an acid. Blue litmus paper will turn red in an acid, but it'll stay blue in a base. So indicators will react differently depending on whether you have acids or bases, and those are great ways to tell your substances apart from each other. So I mentioned pH before, and pH really stands for power of hydrogen. It's a measure of acidity. And so the pH really is a way to represent the concentration of hydrogen ions or hydronium ions, so H plus, in a solution. And so you can see our scale over here. It ranges from, practically speaking, 0 to 14. And it's used to classify substances as either being acidic, basic, or neutral. So if you're below 7, you're acidic, above 7, you're basic, and at 7, you're neutral. So below 7, your concentration of H plus is more than your OH minus. For example, lemons, pH of 2, that's acidic. pH is equal to 7, your H plus is equal to OH minus. So you're neither acidic nor basic. Great example here, pure water. If you look at the pictures, you'll see the OH is equal to the H plus here. Here on the acid, you'll see the H plus is greater than the OH minus. And lastly, for basic, pH is more than 7. The OH concentration is more than H plus. Good example would be, if we look here, pH of 10, soap. So the smaller your pH, the more acidic you are. So 0 is very acidic. 6 is still acidic, but not as acidic as 0. And the larger your pH, the more basic you are. So 14 is very basic. And then, 8 is basic, but just not as basic as 14. Your blood is slightly basic. It's just a little bit above 7. So even being a little bit above 7 still makes you more basic compared to being acidic. So there is a way to calculate pH. We're going to review this later on, so don't worry about it too much right now. We're going to go over a couple ways to determine the pH of a solution. One way is using a device called a pH meter. It's just a device that you stick into your solution with a probe, and then the pH appears on the screen, and you can tell if it's an acid or base. The other way, as I mentioned previously, is an acid-base indicator. It's any substance that'll change color in the presence of an acid or a base. So as we saw earlier, if you have blue litmus paper and you dip it in a substance and it turns red, then you know that substance is an acid. But if you have red litmus paper and you dip it in a substance and it turns blue, then you know that substance is a base. So typically when you're testing solutions out, you want to use both red and blue litmus papers. And the reason why that is because let's say you have a neutral solution. The blue litmus paper will stay blue in it, and the red litmus paper will stay red in it. If the blue litmus paper stayed blue in something, you can't right away say it's neutral because it could be a base because blue stays blue in a base. And if the red stayed red in something, you can't say it's neutral right away because, well, red stays red in an acid. So what you need to do is you need to test your substances out with 2 pieces of litmus paper, one red one blue one, and see what happens. If neither change, it's neutral. If only the red changes to blue, then it's basic. And if only the blue changes to red, then it's acidic. And that's all written down for you over here. So we have a few practice problems here. A blue litmus paper is dipped into an unknown solution. The blue litmus paper turns red. Is it an acid, base, or neutral? So we know that would make this an acid. You can pause the video and try these yourselves. A blue litmus paper is dipped in an unknown substance. The blue paper stays blue. Is it an acid, a base, or neutral? So right now you can't really tell. It could be a base, it could be neutral. We know it's not an acid because it stayed blue. Blue litmus paper stays blue and bases are neutral. So we'd probably have to go test it out with a red litmus paper. And like I said, if the red changed color to blue, then it's a base. But if the red stayed red, then it's neutral. There are other indicators out there. Litmus paper is just one type. There's basically 2 colors. It tells you if it's an acid or a base. There's another type of indicator called universal indicator, which is a mixture of different indicators, and it changes into a whole bunch of different colors. And so it gives you a greater range of colors, and it gives you more specific pH values. pH paper is dipped in universal indicator, and what you do is you basically take the paper, dip it in your substance, it changes color, and you match it to a chart given to you. So for example, if the color was, let's say this over here, after dipping it into a solution, then I would know the pH is 4.5 and it's acidic. So universal gives you a more specific pH than litmus paper. So for example, if we look at these questions here, you can pause the video and try it out yourself. Which test tube contains sodium hydroxide? Which test tube contains hydrochloric acid? Well, let's look at the color of the paper. Here, this is green. This is a pH of 9. So we know this is a base. Here, this is red. So it's pH of 1. So we know this is an acid. So now you just have to make the connection. Hydrochloric acid is the acid, and the base is sodium hydroxide. So the indicators are quite useful in labs when you're dealing with substances where there isn't much of an indication as to what something is. Way better than tasting it, which you should never do. And then there's other indicators that exist out there as well. There's indicators that are In their liquid form, you could add a drop to your solution. It'll change color as your solution changes in its acidity. So these are a whole bunch. You don't have to memorize these. One that you may have used in the lab already is phenolphthalein, the one that turns pink when you go basic. So for example, if we look at phenolphthalein here, the color changes from 8.2 to about 10. So it goes from colorless to pink. So once this becomes basic, this will become more of a pink color. And that'll be important because we're going to be discussing indicators in more detail this year in grade 11 chemistry. So if a solution has phenolphthalein in it and there's a pH of 10, we know it would be pink because the color change happens from 8.2 to 10. So beyond that, it'll still be pink. You can pause the video and try question 2 here. What color would bromothiamyl blue be when pH is 13? So you have a solution with a couple drops of bromothiamyl blue. Solution has a pH of 13 now. What color would it be? So let's see the color changes as the pH increases. The color change happens from 6 to 7.6. That's when it'll start to change color. And beyond that, the color is now sort of permanent. So it goes from yellow to blue in the higher pH range. So that means that the bromothiamyl blue will be blue when the pH is equal to 13. But let's say our pH was 5, for example, then our bromothiamyl blue indicator would be yellow. So different indicators change different colors. We use them for different reactions, but they're still kind of the same concept. You don't have to memorize these right now. Just know how to apply this information. And then lastly, there's neutralization reactions. Remember, we discussed these as being a special type of double displacement reaction. It's a reaction between an acid and a base, and it produces water and a salt. Our general equation for an acid-base reaction, a neutralization reaction, is acid plus base produces water plus salt, which is just an ionic compound. And so really what's happening is your pH of your acid is less than 7. Your pH of your base is more than 7. And then in the neutralization reaction, the pH is, at the end afterwards, a bit closer to 7. It could be right on 7, but it could be just closer to 7 than it was before. Because what's happening is the H plus in the acid and the OH minus, they're basically combining to cancel each other out as H2O. So here you can see you have HCl, which is a pH of less than 7, and NaOH is a pH of more than 7 because it's the base. I know that from the OH here. And they're going to produce some water in a double displacement reaction, plus some NaCl. And so we already went over these reactions in a previous video, but now the pH is closer to 7, which is why we call it a neutralization reaction, because it's closer to neutral now, or it is neutral. So here there's just a few practice examples that you can go over. You can pause the video and then check with me to see if you're on the right track. You need to identify the substances as acids, base, salt, and water. So I'll start off by identifying all the bases in the reactions. Anything with OH here is a base, so base, base, base. And then our acids are the other components. So it starts with an H in the front. Acid, acid. And then H2O is our water. And then we have our salts. If you look at a neutralization reaction, it falls under one of these, is a special case of one of these. And you would probably know that it is a double displacement, the special case of that, because we have a metal switching spots with H in a compound. And then you should be able to predict some simple neutralization reactions. So here I have an acid, here I have a base. Just make the H switch spots with the metal. And so we get NaNO3 aqueous plus H2O liquid. Here's same idea. The H goes where the Ca was, the Ca goes where the H was. And so we get CaCl2 AQ, I did the crisscross there, plus H2O. So very straightforward, acid plus base gives you salt plus water, pH closer to 7.